Hello everybody, welcome to lesson 5. This is the last lesson of acids and bases. Today we will be talking about the Arrhenius and the modified Arrhenius theory. Before we get into that, we are going to do some review. The question says, a solution with a pH of 10 is diluted to have a pH of 6. Does acidity increase or decrease? So remember, on our pH scale, as the number decreases, acidity increases. So more acidic, pH decreases. So in this case, acidity is actually increasing. Now, what factor does it increase or decrease by? So 10, 9, 8, 6. Okay, that's times 10, times 10, times 10, times 10. 10 times 10 times 10 gives me 10,000. So it increases by a factor of 10,000. Okay, the next one says, using the following data, determine the pH and the hydronium concentration of the following unknown. Here is the data. The solution turned Alzarian yellow, yellow. So if I'm looking here on our data booklet, Alzarian yellow is yellow when it is below 10.1. Okay, so let's get our scale going here. There's about 10.1, and it's less than 10.1. Great. Chlorophenol red turns the solution yellow. So let's find chlorophenol red. So when it is chlorophenol red, it is going to be less than 5.2. Okay, so we find 5.2, you just eyeball it, and it's going to be less than. Bromocresol green, the solution turns green. So we find bromocresol green, and it turns green. That means it's in between 3.8 and 5.4. So I'm going to find 3.8 and 5.4. So when it's in between, we close the box. And the last one is methyl red. The solution turned orange. So we find methyl red, and it's orange. So it's in between 4.8 and 6. So 4.8 is going to be about here, and 6 so there, and we connect the two. So now you're looking for where you see 4 lines overlapping. And I see 4 lines overlapping right here. The reason why I'm saying 4 is because we have 4 indicators. You want to see where all 4 of those overlap. So pH, the range is 4.8 to 5.2. Remember, you have to report a range, otherwise we're not sure. It's somewhere in between that range, so you have to report the full range. Okay, and lastly, to find the hydronium concentration, you're going to go 10 to the power of negative pH. This one gives me 1.6 times 10 to the negative 5 moles per liter. And then this one here, actually we need to report to one significant digit. So this is actually going to be 2. And then here, 10 to the power negative 5.4, no, 5.2 equals 6 times 10 to the negative 6 moles per liter. If we were to list this from biggest to smallest, we would say that our hydronium ranges from 6 times 10 to the negative 6 to 2 times 10 to the negative 5 moles per liter. So there is our hydronium range. Okay, let's talk about what this lesson is about. Learning goals today. Describe what makes solutions acidic and basic. So before we were determining whether a solution was acidic or basic by its pH, by its properties, but now we're going to look at it from a reactions point of view. Describe the roles of an acid and base in water, and describe strong acids and strong bases in solution. So let's go ahead and get started off with our strong acids and strong bases in solution. Strong acids and bases will fully 100% ionize or dissociate if it is a base. Weak acids and weak bases are going to ionize to approximately 50%. Strong acids are the first 6 acids on page 8 of your data book. So if you go to page 8 in your data book, and you'll see that the first 6 right above the hydronium ion, those are considered strong acids. So I'm talking about, let's see if I can rotate this, yes. So perchloric acid, hydroiodic acid, hydrobromic acid, hydrochloric acid, sulfuric acid, and nitric acid are all considered strong acids. For example, nitric acid, HNO3, and HCO4, this is perchloric acid, are considered strong acids. Okay, what about something that's weak? So we can just go anything underneath that hydronium ion is considered a weak acid. So formic acid, HCOOH, is considered weak. Sulfuric acid sounds pretty deadly, but it's also weak, still considered pretty dangerous, but it is a weak acid. Strong bases are any compounds that contain the hydroxide ion. For example, NaOH and potassium hydroxide are considered strong acids. Ammonia, NH3, ammonia is considered a weak base. This is probably the only 2 types of bases you'll know. You'll either see something with hydroxide or you will see ammonia. We'll talk a little bit more about different bases when we learn about amphiprotics. Okay, let's talk about Arrhenius. Arrhenius described Arrhenius defined a molecular compound that ionizes. Basically, he says an acid that ionizes in water to produce H plus is considered an acid. Okay, so for example, let's have HCl. HCl, aqueous. Now this is a strong acid, so I'm going to write 100% ionized over the arrow, and it produces H plus and Cl minus. Because it produces H plus, that defines it as an acid. Let's do this with one more. Let's do this with a weak acid. Let's do it with formic acid, HCOOH, aqueous. It's going to be less than 50% ionization. It's going to make H plus and COOH minus. One of those hydrogens are coming off. Let's move into bases. Arrhenius defined a soluble ionic compound that dissociates to produce OH minus in the solution. So let's take a look at NaOH. NaOH is going to be a strong base, so it's going to 100% ionize and form Na plus and OH minus. Okay, but what about ammonia? Ammonia, I told you earlier on, is considered a base. But does Arrhenius' theory make sense? So basically, ammonia is considered a base. A base. But however, does not produce OH minus. So was Arrhenius' theory actually correct? So then we had to modify this theory because we know ammonia is a base. When we test it with pH paper, it turns out to be a base, but it does not produce hydroxide. So how is it that it is a base but is not producing hydroxide? So basically what we had to do was Arrhenius had to have his theory modified. The theory was modified where dissolved substances collide with water. So now instead of just kind of ionizing or breaking apart, it is now reacting with water. When it collides with water, it's going to make one of two things. It's either going to steal or donate hydrogen to water molecules. Acids donate hydrogens. So they're going to donate a hydrogen or a proton to the water molecule. So for example, HBr is acidic because it donates hydrogen to produce hydronium. So this is what it looks like. HBr, aqueous, reacting with water. Okay, I'm going to grab another color here. So because it's an acid, you're going to look at your species here. It can do one of two things. It can either gain another hydrogen or it can give. You can only gain in certain circumstances. Right now, remember back to bonding, HBr cannot accept another one. It's bonded out. It can only have one bond. So what happens when it collides is that hydrogen is going to go over and react with water, okay? And these are all going to be equilibrium reactions, so we will draw the double arrow. And produce hydronium and Br minus. So now there are two ways to see if it's an acid. It produces hydronium and it donates a hydrogen. Okay, so donates H plus to produce hydronium. Now let's talk about bases. Bases, steel. So think about baseball, bases, steel, hydrogens. For example, ammonia is basic because it steals hydrogen to produce hydroxide. So you have NH3, aqueous. Oh, sorry, water should be liquid, plus H2O, liquid. Of our equilibrium arrows. And what happens is this nitrogen is not going to give up anything. It can't really give up a hydrogen. It would be very unstable. So what it's going to do is it's going to steal a hydrogen from the water to produce ammonium, which is an ion we have seen before, and OH minus. So this is the only exception where it forms ammonium. So this is two ways to tell that it's a base. It steals H plus, and it forms to produce hydroxide. So this became a more universal theory, therefore why it was modified. Okay, so now that we kind of get the gist of what acids and bases are, we're now going to talk about different types of acids and different types of species in water. The first we're going to do is compare monoprotic versus polyprotic acids. So just like our indicators, if we have a monoprotic acid, that means it only has one hydrogen. They react with one molecule of water to produce only one hydronium ion. For example, HNO2 is a monoprotic acid because it only has one hydrogen. So if I were to react this, it would look something like this. HNO2 aqueous would react with H2O to produce hydronium Okay, because it's an acid, it's going to be donating its hydrogen. Hydronium is an aqueous substance plus NO2 minus. Okay, so it can only partake in one reaction. Now, nitrous acid is a weak acid, so it's going to ionize approximately 50%. Sorry, that should be equilibrium arrow, approximately 50% ionized, because it's a weak acid. Now, there are polyprotic weak acids, and just like our polyprotic indicators, polyprotic acids are going to have more than one hydrogen. It can react with water more than once. However, only the first reaction is very significant. For example, so phosphoric acid, H3PO4, is polyprotic because it has more than one hydrogen. Now, this is what we're talking about. In the past, okay, so in the past, we wrote our reactions kind of like this. H3PO4 aqueous ionizes to produce 3 hydrogen ions plus 1 phosphate ion. There. So basically, this is kind of a net reaction. This is the overall reaction. Overall, this is what happens. But I'm going to show you the steps that happen to get here. So let's kind of separate that. You'll notice that chemistry, as you learn it, you're going to learn that you're learning things that aren't 100% chemically backed up in Chem 20. And that's okay. That's just we're trying to get you the general idea of chemistry. And then as you guys go through your chemistry education, you'll begin to actually learn the background behind it and what it actually means. Now, what happens is H3PO4, so phosphoric acid, reacts with water. And equilibrium arrows. And our hydrogen is donated to produce H3O plus aqueous plus, and then we lost one of our hydrogens, so it becomes H2PO4 minus. Okay, now this guy here, because it has a hydrogen, it can go through it again. H2P4 aqueous minus plus H2O liquid, donates another hydrogen, produces another hydronium, and now it only has one hydrogen, resulting in a 2 minus charge. Okay, now this can happen again. I can take this species here, and it's going to react with water again. HPO4, 2 minus, aqueous, reacts with water. Equilibrium, basically an equilibrium arrow means that the reaction can go forwards and backwards. So on one side, it's gaining the hydrogen, but on the other side, it can gain a hydrogen back and then go back to being phosphoric acid. HPO3, it's going to donate another hydrogen, gives me H3O plus aqueous plus PO4 3 minus. Okay, so notice how we produced hydronium 3 times. Notice how our end product at the last reaction was PO4 3 minus. Okay, the reason being is because this will make this is making a net reaction, and we'll talk a little bit more about net reactions in the stoic unit. But basically, in an acid-base reaction, this first reaction is significant. It is the most significant reaction. It determines whether or not you have a strong acid or a weak acid. And it's because it produces the most hydronium concentration at this point. The other reactions, they produce a significantly less. And this will make more sense, and we'll go into more detail about this in Chem 30. Okay, lastly, we're going to talk about amphiprotic substances. Amphiprotic substances are substances that can behave like acids and bases. So they live on both sides of the world, okay? Depending on what the reaction is looking like, they can behave as an acid if you need them to, they can behave as a base, or whatever they're feeling when they're in the water. So let's talk about an amphiprotic substance. An amphiprotic substance can either donate and steal protons or hydrogen ions. For example, because HSO4 minus has a negative charge, that means it can steal a hydrogen to become a base and become a base. Let me show you. HSO4 minus reacts with water. It steals a base. It steals a hydrogen. And then it becomes H2SO4 because it stole a base. It stole a hydrogen. And because we stole one hydrogen from water, it becomes hydroxide. Okay, so this means that it can be a base. Now, but since HSO4 minus has a hydrogen atom, it is also able to donate a hydrogen to become an acid. Let's take a look at this reaction. HSO4 minus aqueous plus water. Now, instead of stealing, it's now going to donate. It donates. It becomes H3O plus, so that the water gained, so it became hydronium. And because this substance lost a hydrogen, it becomes SO4 2 minus. Remember, when you lose positivity in your life, you become more negative. So notice how this substance can go both ways. How do you identify something that's amphiprotic? Well, first of all, you know something is amphiprotic if it has a hydrogen and a negative. Okay, if it has a hydrogen and a negative charge, it is capable of being a amphiprotic substance. Okay, so write an equation to show that lithium sulfate is an acid. Oh, sorry, it should be lithium hydrogen sulfate. Lithium hydrogen sulfate. So you're first going to write a dissociation reaction. So step 1 is a dissociation reaction. You want to see which ions you are working with. So I go LiO, lithium hydrogen sulfate. Looks like this. Beautiful. HSO4 aqueous. We dissociate it. Li forms a lithium ion plus HSO4 hydrogen sulfate aqueous. Now you're going to choose either something that has a hydrogen in it or something that has a negative in it. So that rules out lithium. We can't really use lithium. It's not going to help us determine if it's an acid or base. So we look at this guy here, our hydrogen sulfate. Then you're going to take your hydrogen sulfate and write a modified Arrhenius. Now we're trying to prove, oh, that is done very badly. Modified Arrhenius. So we need to prove that this is behaving like an acid. So that means it needs to donate a hydrogen ion. So SO4 aqueous plus water, equilibrium arrows. Now we want to prove that it's an acid. So I'm going to show it donating a hydrogen to produce hydronium and sulfate ion. Okay, let's do another one. Write an equation to show that potassium carbonate is a base. So the first thing you're going to do is write a dissociation reaction. So 1, dissociate. You're going to take your potassium carbonate, C2O3 aqueous, dissociate it. I form 2 potassium ions plus a carbonate ion. Then you're going to take something that either has hydrogen or a negative ion or both. So in this case, it's the carbonate ion. Step 2 is modified Arrhenius. So I'm going to take my carbonate ion CO3 2 minus aqueous, react it with water, equilibrium arrows because they can go back and forth. And in this case, we are going to steal a hydrogen. It becomes HCO3. Because we gained a proton, a positive ion, it makes us slightly less negative in our life. We gained a little bit of positivity, we become slightly positive, plus hydroxide. Okay, and that proves that it's a base. Okay, the last one is the U-try. Could sodium phosphate be an acid or a base? Write equations to prove your answer. I'm going to give you a moment, and when you're done, you can unpause and check your answer. Okay, so first step you're going to do is write a dissociation reaction. We want to take something that has a negative charge or has a hydrogen in it. So the only thing I can take is this. I take my phosphate ion and write a modified Arrhenius equation. Now, because there is no hydrogen on my modified Arrhenius equation and it only has a negative charge, the only thing that it can do is steal. And because it is stealing, it's going to produce hydroxide, meaning that this substance can only be a base.